And the reality is that everything is basically a guess.
Okay. Yeah, let me just clarify. A well-educated guess?
That depends on who you're asking, basically. But I guess some guesses are better than other guesses.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're chatting to Oskar from Elmer Racing, joining us all the way from Finland. Elmer Racing is a producer of bespoke billet race engines. In particular, these engines are used in a variety of forms of motorsport. Most specifically, we know the Thor engine that they produce because it holds the world time attack lap record, which we'll talk about as we go through our interview with Oskar. There's a lot to take in here, particularly when it comes to the design and the development, as well as the construction and maintenance of a billet engine. We've seen billet race engines pop up across all forms of motorsport over the last 5 to 10 years. They have become a bit of a buzzword. But when we get down to the nuts and bolts of these engines, there is definitely a power level where billet engines just make sense, and there are going to be purists who argue that the car is no longer a Supra if it's not powered by a cast iron block 2JZ, or it's no longer a Nissan GTR if it's no longer powered by a factory cast alloy VR38. And I'm not really getting into that argument. It just gets to a point where if we want to go faster, we're going to need components that are going to hang together and be more reliable. So a really interesting chat with Oskar about what goes into the design and development of his particular engines. Now, just for those who maybe aren't aware of what High Performance Academy is, just briefly, we are an online training school. So we specialize in teaching people how to essentially make your car go faster, all manner of automotive performance. Specifically, we focus on engine tuning, both aftermarket standalone as well as factory engine management tuning. Performance engine building, obviously pretty relevant to today's task, today's conversation. We also cover wiring and driver education and car setup. Specifically, I just wanted to talk a little bit about a course that is really relevant to today's topic, which is our practical engine building course. This is something that I know a lot of enthusiasts tend to consider as outside of their realm of capabilities, and they will entrust their engine build on their project car to either a local performance workshop or maybe their local engine reconditioner. Sometimes that works great. However, sadly, I've seen so many horror stories come up where people have spent their hard-earned cash, entrusted their performance engine build to one of those two that I've just spoken about, and end up with a really subpar result. The reality is, though, it's something that is definitely not too hard for the average enthusiast to do, provided you've got a bit of an eye for detail and a bit of patience. The other good news is that you're not going to have to spend thousands of dollars on specialist tools in order to do that. So our practical engine building course gives you an understanding of what we're actually trying to achieve when we're building a performance engine, how we may need to vary certain aspects such as the clearances inside the engine in comparison to what was suitable for a stock engine making factory power at the factory RPM limit. We also produce a 10-step process, and you can apply this irrespective of the engine you're personally building. This 10-step process covers the entire engine build from the strip down and inspection through to machining, selecting parts, cleaning, and finally assembling your engine and starting it up for the very first time. We've also got a library of worked examples where you can watch that 10-step process being applied from start to finish. As an added bonus here, as a HPA Tuned In podcast listener, you can use the coupon code podcast75. That's going to get you $75 off the purchase of your very first HPA course, and we'll chuck a link in the description you can follow. All right, with our brief introduction out of the way there, let's get into our interview. All right, welcome to the podcast, Oskar. Great to have you joining us today. And can we start by just talking a little bit about what Elmer Racing is and what you do?
Yeah, nice to be on here. So Elmer Racing, well, we currently sort of primarily try to focus on making complete billet racing engines maybe not only for racing, but that's what we currently do. And we do some racing components also. So billet merge collectors and some custom intake manifold designs and stuff like that also, that we're continuously working on trying to improve the efficiency of all of that really.
Now, being a bit of a detective myself, I can tell from your accent you're not from around here. Can you give us a rundown on where you're joining us from in the world today?
Well, our current work location is in Finland here, so we have a nice, cool -17 degrees outside here at the moment.
Sounds balmy. I'll enjoy our summer rather than your winter then.
Yep.
Now, on this side of the world, you're probably best known for your success in the World Time Attack Challenge category, run every year until recently over at Sydney Motorsport Park in Australia. And currently your Thor billet engine powers the RP968 Porsche, which holds the, if I'm right here, the tin top outright lap record around Sydney Motorsport Park, and also just barely pipped for outright lap record by Nico Hülkenberg in an A1 GP car. So anytime you can get a modified production road car within touch of a wings and slicks race car driven by an F1 driver, that's pretty astonishing. Now, obviously, there's a lot that goes into getting that lap time, the driver, the car, the suspension, but definitely, as we've seen over the years, we've been following World Time Attack. Engine performance and engine power has just spiraled out of control. Can you start by talking to us about how you got involved with the RP968 project? Okay,
sure. So Rod, of course, the mastermind and boss behind the whole RP968 is, I think, went kind of a little bit out on a limb there, sort of talking to us with that engine. We were at the time looking at doing billet blocks because we saw that, okay, this is like the easy thing to get started and to make components for racing engines and all that good stuff. Mm-hmm. And we started looking into doing with a local customer or a sort of a collaboration partner or something like that here in Finland that was doing rallycross at the moment and doing a complete rallycross engine for them, because we saw some significant improvements could be done on that. But that team sort of their continuation in the rallycross stuff fell through a little bit, and actually at the same time was over at World Time Attack with some other Finnish guys. We had two guys from Finland there competing in, I think that was 2016 or something. So went over there with them and said hi to everyone, and met Rod there and spoke a little bit about the block situation. So they wanted more power from their 968 engine, but it is the block is a known failure point at around 800-900 horsepower, and they wanted more than that. So we looked at the block and we can looking at the dimensions on that block, so Boar spacing is really long or relatively large on that block, but the cylinder size is not that large. We're like, okay, I mean, if we do a complete cylinder head also, we can flip the intake and exhaust over to the other way that they do that to fit a larger turbo in the engine bay and all that stuff, like already out of the box, so they don't have to have a factory head that they flip around and do manual changes to that, and it'll overall be a much better package. And at that time also they had been on the RP968, the car basically continuously redeveloping things as they conclude that, okay, they need to get these parts of the car better and this better again, and then they end up with these kind of legacy parts that end up sort of not being optimal compared to doing it right from the start. Start with it would make sense to just do a complete engine. We could get so much more potential out of this. It would be so much easier to tune and much less sort of potential failure points. So we can, if there are any issues, we can fix anything because we'll be the OEM manufacturer of the whole thing, basically. Sure. And he concluded, it makes sense to do that. So then we started looking at the specs and started pushing the design and going for that for their car.
All right, there's a bunch of stuff I want to sort of head back and unpack in there. So one of the questions I've got, it sounds like you did design this engine to essentially be backward compatible, I guess, would be the best term of using with the original Porsche engine. If I'm right there, when you're looking at doing everything custom, including a cylinder head, where is the line between keeping backwards compatibility with the factory Porsche geometry, at least to some degree, versus something that's completely bespoke, just a clean sheet of paper design with no factory comparison to the original Porsche engine at all?
Well, component-wise, there's not really much to take into consideration with that. Of course, we had the stringent World Time Attack engine rules for the Pro class to take into consideration that limited us severely. So,
what are those limits? Just so we know what you're dealing with there.
So that's basically a one-liner that says the engine has to be based on a factory engine. So that basically said that, okay, like we can't put a V7 engine in there with like with a super turbocharger or something like that. Well, we could probably, the boost section we could probably, but yeah.
Yeah. So it has to at least be somewhat relatable to what was originally in the vehicle. Yeah.
So we basically chose to keep the original bore spacing, to keep the engine mount locations, bell housing fittings, of course, use factory, factory like blanks, or not factory blanks, but factory compatible blanks for the camshafts and that kind of stuff. So it does share like lots of geometries, even though there isn't like basically a single part from the original engine, but it still has like shares sort of dimensional wise and layout wise quite a lot actually with the 968.
Okay. All right. Now you mentioned bore spacing, and I'm assuming that why that's important is that's going to drive what you can use in terms of a maximum bore diameter while still retaining sufficient strength or material between adjacent bores.
Yeah, that is correct. So, and that also is something that will limit valve size, of course, which is really one of the major factors for engine design and RPM range and stuff like that.
Okay, so that then drives the next question. You've got a bit more freedom around bore and stroke over what the original 968 engine used. And these decisions that you make, particularly with stroke, then you've got the rod to stroke ratio to consider, and these both kind of drive what your maximum RPM ceiling's likely to be. So how do you weigh up these design parameters when you're deciding? Obviously, the old saying goes, there's no replacement for displacement. Well, we have boost now, so that's arguable, but definitely there can be some significant upsides in terms of boost response with a large turbo when we've got more capacity to drive that turbo in the first instance. So, can you give us a bit of an understanding of your design philosophy around the bore to stroke versus the outright capacity?
We basically. So our goal, of course, depends on what you're designing the engine for. For these racing type engines that we're currently working on, you really want to get the best power to mass ratio you possibly can out of the package. And then there are other parameters that are not as important, like external vibrations, for instance, on the engine and fuel economy, all of this stuff, of course, it has some kind of influence, but it's so small that it is like virtually zero, especially for time attack, we only need to carry fuel for the out lap, flying lap, and the in lap. So if you can reduce fuel consumption by 5% or whatever, that's not going to make any kind of measurable influence at all. If you can like reduce the engine weight by 200 grams, that's probably going to be like worth more. So we basically want to pack as big of a bore as we can possibly fit in the engine sort of exterior size, so that allows us to run as large valves as possible, and the valve size is ultimately what's going to be the limiting factor, because with displacement that doesn't really help if you don't like have the RPM also. So you want the basically a really high naturally aspirated power, so then you don't need to add as much boost on top of that to get the whatever power level you want to be at. And the less boost you need, the less ECU tuning problems there are, the less sort of anti-lag stuff you need, and it's like a much easier setup overall. You have lower EGTs and everything lives longer and everything gets easier, sort of the less boost you need. So
I think it's probably fair to say that the mainstream philosophy around, well, that I see at least in World Time Attack, has been take a factory engine, probably these days, replace the factory block with a off-the-shelf billet, and then put a large turbo on that engine and jam as much boost into it as you possibly can to get the power you're targeting. So your philosophy's been almost the opposite. Build a very high powered, naturally aspirated engine, and then use a small amount of boost to get to your power target.
Yeah. Although, I mean, looking back on it, like with starting from a complete blank sheet, for instance, I don't think our Thor engine is optimal for time attack use. It's too powerful for that, really, because the sort of amount of boost you can like sort of dial down to, like once you start going below sort of 250 kPa map or something like that, then the lag isn't really that much of an issue anymore below that. So you want to be able to use at least that much boost pressure, really. And our engine basically produces too much power to be usable at that boost amount. So you would probably want to run like
problems with wheel spin.
Yeah. So at lower speeds, traction issues, and then at higher speed, tire longevity, because they run so insane amounts of downforce that the more power you push into the car at high speed, you get more speed and more downforce, and then you end up crushing the sidewalls on the tires, and you end up starting delaminating the layers there and the sidewalls, and the tire, of course, comes apart after that. So limited on
we have
both sides.
Yeah, we have definitely seen. It appears that World Time Attack's probably starting to edge towards finding the limits of a DOT-approved tire. So we'll see how that pans out. But that's an issue, but probably not our main sort of angle for today's interview. So just coming back to the capacity, I am definitely not a Porsche 968 fanatic, so I don't know too much about the stock engine. Can you give us the stock capacity versus what your Thor engine is?
So I think that I'm not super well sort of memorized on that, but I think the 968 engine is basically based off the 924 and 944 engine, which I think was about a 2.8 liter or something like that, and then was bumped up to 3 liter displacement. And yeah, we bumped that up, so with the same exterior dimensions, to 4,000 cc for our Thor engine.
So 4 liter from 3 liter. So that's a pretty significant improvement for a 4-cylinder engine.
Yeah,
and it makes for a very large capacity 4-cylinder.
Yeah, and that's something you can't really do without going with a custom cylinder head, because there's not going to be any material to seal against anymore with the bore size we want to run. We could increase the stroke, of course, also even further than what we have currently. But again, I mean, for time attack use,
what's the stroke at the moment?
I think we're at 96, 94 millimeters. Wait, I have that open here. Let's see if I have that on our website or not. Actually, I don't think we have that here. Something around that range anyway.
Okay. And what does that allow you in terms of an upper rev limit?
Well, they have run the RP968 to 8,500, but we would expect for drag racing use probably 10,500 would be a more realistic value for that.
Okay. Which is interesting, because I know with that engine, you do have some sort of suggested upper limits for power, and you do separate these between sort of circuit use, time attack use, and drag racing. So what's your sort of suggested limit for the engine for those two applications?
So for circuit racing use, so that's like a continuous use at a power level, we recommend 1,500 horsepower for that. And for short duration use, where we're not sure about the sort of thermal balance and stuff like that, and you need to run the RPM really high to reach that, we recommend about 3,000 horsepower would be our sort of estimate for drag racing use for that, with the increased RPM range. And then, of course, that requires more turbocharger RPM and boost from that also to reach that power level. So that makes it impractical for circuit racing use. But of course, again, for time attack use, probably optimal engine would be smaller than this, because it's again too powerful with the sort of power output. So, but yeah, a 3-cylinder Thor engine would again have some more balancing issues, so not ideal either.
I mean, on the electronics front, though, we do have a lot of control at our fingertips in terms of manipulating drive-by-wire throttle opening, boost pressure, etc., to help tame down an engine that's producing too much torque at lower road speed. So I assume, given the results, the PR Tech team that run the 968 Porsche are probably all over that.
Yeah, I think that was one of the things that they're working on now for originally the 2021, but now the 2022. What was it? Beginning of April, I think. Race as it's currently scheduled. So that is one of the things they're working on now, to be able to get the boost control to keep boost much lower as required at the lower RPM. So that makes tuning much easier, basically, than having to run a blow-off valve sort of partly open to limit boost pressure, or like do ignition curves or stuff like that. It's just a sort of less laborious way to manage power. And of course, with drag racing use, you couldn't do that because you need to ramp up the power probably faster during the run than that would be possible. But for circuit use where you can't put down, or you can't accelerate that quickly, then you can ramp in power much slower. So doing that with boost makes sense in that application.
Yeah, absolutely. So it's coming back to your initial design for the Thor engine. So you mentioned that the factory engine in the 968 had some known weaknesses. So if someone's looking at development of an engine and they aren't necessarily sure what the failure points are going to be, what sort of validation do you do, or how do you go about finding out where those weak points are going to be, so that you can address those and make sure that they're dealt with when you're building a bespoke block?
That's excellent question. I kind of want to say that I have no clue actually about that, because it's not really what we do. But of course, I mean, some sort of general assumptions. I mean, if you're really sort of looking into doing a project as cost effective as possible, I would say that sort of if it's not extremely well known issues with the current package you have, and weight wise it's like suitable for your use, then I would say just push it harder, keep pushing it until something blows up. Then figure out, okay, like is this something that we can address or not, or is this actually going to limit us from reaching our target power or not? And then based on that, sort of decide on how to go forward. Because sort of trying to analyze OEM production components sort of non-destructively is extremely time intensive. So I think blowing it up is much more sort of overall a much cheaper and effective way to do that than trying to sort of calculate things or anything like that from a OEM thing.
I think, we talk about people learning to tune by blowing up engines. I just want to be clear that that's a very different angle we're talking about here. We're talking about destructive testing to find the power and torque limits or cylinder pressure limits of an engine, which is a very different aspect. And I mean, I think, not that I am a mechanical engineer, I guess that makes a lot of sense when, if you look at software validation of these sorts of things, ultimately getting the details from an OE engine to be able to develop a good model would probably be difficult, if not impossible. So I guess you're probably dealing with a situation of garbage in, garbage out. So how useful is that model when you can actually do some real world testing? And the other thing that's really relevant here is, I mean, if you're dealing with a popular engine that is well developed in the aftermarket, usually these things are fairly well understood because you're going down a path that's well trodden. So you can learn from the expense of other people's mistakes and understand where these engines fail.
Yeah, that is, of course, also something to take into consideration when you're looking at what other people are doing and where the sort of limits are, like to figure out, like, okay, like what kind of way are they pushing the limits at? Like if they're just running MBT timing and blowing up engines at some specific power level, then that basically means, okay, cylinder pressure, whatever, 250 bar or whatever is causing the issues. Then, okay, if you just limit yourself to 249 bar, but run the engine much less efficiently, so drop the compression ratio, run retarded timing, and much higher boost pressure, you can probably make sort of a rule of thumb would be probably twice the amount of power with the same max cylinder pressure, but your EGTs are going to be the limiting factor at some point, and of course you're going to have horrible lag on the thing. but you can like push things much further if you're sort of aware of how the sort of mechanics actually work, and not just trying to make sort of maximum power capable, but looking at the limiting factor and then pushing that factor up to its limit, and then looking what else can we do to sort of get more power while being under this specific limit.
Yeah, I think something that is easy to sort of overlook is when you're tuning an engine on the dyno and you're optimizing everything. You just mentioned that term MBT, which is where we're basically optimizing the timing until the engine is making peak torque or maximum torque at each point through the rev range. So basically the timing is then optimized, assuming that we can get there without encountering knock. And peak torque, or peak cylinder pressure, as you sort of more correctly say there, that's going to be a limiting factor for component failure. But what we also see, if you look at a torque curve, obviously it starts low, it comes up and it peaks somewhere maybe middle of the rev range or a little bit lower, and then naturally the airflow through the cylinder head starts to fall away and our torque drops away. So what we can find is an engine where we know there's a limit on how much torque we can actually make on the dyno while holding the rods together. Well, what we can do is artificially limit that peak torque value, and then higher in the rev range, we can then basically increase the boost pressure or optimize the timing, or both, in order to basically hold that torque relatively flat. So what that does is actually produces more power higher in the rev range.
Yeah, you could definitely do that also. But what I'm talking about is also making more torque while maintaining your cylinder pressures under peak levels, which is also possible. Just doing that sort of later in the stroke, or later in the combustion stroke. So you basically, for MBT, you typically will have like a peak pressure around like 12, 15 degrees after top dead center or something like that. But moving that later to like 30 degrees or something, then you can push much higher torque output from the engine while still maintaining the force levels at the same level.
But because that combustion's happening much later in the cylinder, in the combustion cycle, that's why you're then creating a lot more exhaust gas temperature and a lot more inefficiency. You're not actually extracting as much power out of the fuel and air that's being combusted as it potentially could offer, but you're holding the engine together.
Yeah. So that's only viable for certain race classes, like time attack, for instance. Maybe if you can deal with anti-lag. Drag racing, definitely. Probably some kind of other like drag racing similar stuff, like tractor pulling or something like that. I would assume you could be very happy at doing that also.
Yeah, I think my gut feel there is for circuit racing, the EGT would probably become a problem before you finished a full flying lap if you were running very retarded ignition timing in order to use that tuning philosophy. I don't have any data to back that up.
Yeah, exhaust valves might end up melting before you complete a couple of laps.
It's a valid discussion though, because it's another area where people view tuning and engine design, I think, as black and white, but there are just a whole lot of different shades of grey here. There's no sort of one solution of getting a result. It's just understanding the implications of the tuning philosophy you're applying, how that's going to affect the engine's performance, and how it's going to affect the engine's reliability. And then again, in this instance, just understanding the implications of exhaust gas temperature versus the time that you're running the engine for. Yeah,
those are all like completely interlinked also. So it's not just a question of designing the best engine or like tuning the engine the best way possible. If you can design an engine to take the sort of tuning options into account, and likewise also like you're like collaborating with that, then you can get a much more effective overall package. And that's one of the things we're doing with our own electronics, and of course with the rallycross engine that we originally started with also. So that's like a really overall package thing that needs to be taken into consideration. There are significant gains that could, depending again on the race category. So some categories might have a benefit and some categories not so much.
Well, we'll move on, and actually want to come back a step and just talking about the pros and cons of factory engine blocks versus going billet. I mean, obviously there's a relatively steep expense curve when you go away from the production block, but we've seen, at least in the past, most OE manufacturers tended to favour a cast iron block, which for our performance application tended to work pretty well. Obviously, it's not bulletproof, but cast iron was a fairly strong material, all things considered. Then, for various reasons, including weight saving, most later model production engine blocks ended up going to a cast alloy. So can you sort of talk to us about the pros and cons of alloy versus cast iron in terms of strength, and how both of those sort of compare strength-wise to a billet block?
The cast iron stuff, I'm not actually that super familiar with. I do have some generic values, but I don't really know what the modern sort of cast iron, what kind of alloys they can use and how strong those really are. But for sort of serious motorsport use, that is really too heavy to be sort of a reasonable starting point anyway. So it's not really sort of something that needs to be taken that much into consideration. But thermal expansion wise, there are of course benefits with using cast iron. So for instance, with the main bearing clearances and stuff like that, that is definitely something that would be very interesting to be able to incorporate into a billet aluminum. But unfortunately, thermal expansion rates don't work that way. But then looking at the sort of cast aluminum alloy stuff, aluminum is an interesting alloy sort of casting wise, because the sort of really strong aluminum alloys are not castable at all, or maybe they are castable but just really poorly castable or something like that, so it doesn't make sense. So the alloy strength that we can use we use in our billet engines is improvement on the 7075 alloy, which is probably around sort of 3 times as strong as cast aluminum engine blocks, just the raw material. But of course, the stiffness is basically exactly the same, and thermal expansion rate is actually a little bit worse. So there are some trade-offs there, though.
So, I mean, you're just talking about 3 times the strength, but that's taking into account a like-for-like design, I assume. Then you can
just the raw material
even further. Yeah. Okay. By changing the design. So one of the things with an alloy block is we can't run the piston rings directly on the alloy. So we're talking here about both aftermarket billet blocks as well as factory. There's a variety of options, including sleeves or coatings such as Nicosil, etc. What are you doing in your own billet blocks?
So this is one of the things where there are lots of different solutions, and some solutions that I don't really regard very highly might be absolutely fine for some applications. So just because we're not using something doesn't mean that it's necessarily always bad. But for instance, the wet sleeve type things, for instance, we try to stay away from those as much as possible unless there's some incredibly stringent requirement for that, because that just reduces your overall engine rigidity, or the torsional rigidity of the engine, a lot. So you want to really have the raw block material between the cylinders to keep that as stiff as possible, and that has a really large influence on the overall engine rigidity. So we want to keep that as much as possible. So on our Thor and Rex engines, we run as thin dry sleeves as possible. So I'm not going to go into super details on how thin we dare run those, but we would want to dare to run those even thinner, actually, just basically a coating on that. And for our V6 Hill engine, we're going with plasma spray directly on the block material.
So that sounds like quite a departure from what we see with mainstream aftermarket billet blocks, where most of the manufacturers are running something like a dart and ductile iron sleeve that's then sort of a semi-press fit into the block. So you've gone a very different direction there with this thin dry sleeve.
Well, I mean, that's basically what we use on our Rex and Thor engines currently. So thin ductile iron dry sleeve that is just inserted. We do have a lip on the top also, so it's not just a sleeve, but a lip on the top. But we're moving away from that now with a Hell engine and going with a plasma spray. I think that's the way to move forward.
All right, so just to come back a step, so you said with the wet sleeve, and could you just define for our listeners what a wet sleeve is? and why you've sort of don't prefer that option.
Okay, so with wet sleeve, basically in engines where you have a relatively long stroke, you need to have continuous use. You need to have a cooling in the block itself. And machining that from a billet gets kind of difficult. So you see some designs where you have like a bolt-on, like what are they, like plates from the side or something to seal that up and machine and have those machined from the side. And you see a different type of solutions where basically sort of try to figure, or like how different people try to figure that out in the sort of a most economical and feasible way for their products. And one of the really easy ways to do that is just to machine basically the cylinder section out of the block completely, and then just have wet sleeves. So basically where you have the cylinder on the inside seals to the crankcase, and then wet, meaning that the outside of the sleeve is in contact with the cooling pocket then. So that is basically a wet sleeve, and a dry sleeve will then be completely dry, so it's not in contact with the coolant at any point, so it's completely surrounded by actual engine block material.
So the wet sleeve design, just to sort of sum up what you're saying there, from a machining perspective, it's easier to add a water jacket to a billet block.
Yeah, a lot
then incorporate
easier.
a wet sleeve. Okay,
yeah.
But that wet sleeve is then only supported essentially at the deck surface of the block, and then at the bottom of that sleeve where it locates into the block. So that's where the rigidity and strength lacks over a dry sleeve.
Well, it's not really a problem with the sleeve as such. I mean, those can be easily designed to be strong enough, I think. Although with them being like separate sleeves, like at the joint section, I don't think you could run as thin or like as high of a bore to bore spacing ratio, but probably you could get pretty close to that. But sort of the rigidity that we're after is like the overall engine rigidity. And that if you just have the engine block basically milled out, so you have a square sort of section with a big hole in the middle, where you have in this case, so in the case of our Thor engine, for instance, if you had like 4 separate wet sleeves in there, then the overall package is much less sort of rigid in torsion. So when you're like applying torque from the front of the engine block, that how much the engine, both the engine block and of course the whole assembled engine, like how much that flexes. And that is something that we want to keep as rigid as possible, and as reasonably rigid as possible, of course, and that overall will cause much less issues, and the engine will have a much longer life, so you won't have the problem that you hear about with V8 drag racing engines, for instance, with MID type sleeves, where if the engine is like a half a degree like non-straight, then that's still within tolerances, and you can put it back together again and just put the cylinder heads on, and it will sort of straighten out from the torque of the cylinder heads. But like, that's maybe pushing it a little bit too far for our taste. Like, we prefer things to be a little bit more, and especially for circuit racing stuff where you might have suspension loads and stuff like that being sort of inadvertently going through the engine block, then you really want to have a high stiffness on that.
Yeah, no, that makes perfect sense. I mean, is the dry sleeve option, what's the options there? Let's go back a step. Sorry, I'll get my thoughts in order here. With an individual mid sleeve, we can, if the worst happens and we have an engine failure or something goes bad that scores really badly one cylinder, it is possible to remove and replace an individual sleeve. With a dry sleeve, I assume that's a press fit, essentially, an interference fit into the block. That sounds to me like that would be difficult or impossible, or is it still serviceable in that way?
It is, especially if you don't need to do that trackside, then it's no problem at all. Definitely serviceable. Trackside could be done, but then it would specifically do a relatively low sort of force press fit, which gets kind of difficult with the tolerances, because when you have a round sort of sleeve, it's actually not round, and then once it's very, very thin, you basically sort of measure the circumference of that and fit that into the block, because of course once you put it into a round hole and it's really thin, then of course it's round after that. But getting the sort of a correct press fit for that is kind of difficult, but it is definitely doable. So you can have for instance, for drag racing use, you can have a tool where you can like get the press fit out manually at the track or something like that. It's very doable.
It's one of those things where obviously that's a worst case scenario, and I mean anytime you're trackside trying to replace a sleeve, you're having a pretty bad weekend from the get-go. But even if we're not talking about trackside repair, obviously, people are investing a fairly large chunk of cash into a block or an engine of this nature. So the long-term serviceability, even if it is between races and not trackside, is something that still does need to be considered. I know that you've mentioned the plasma coating for your HAL engine, and we're going to park that for a moment because I've still got a few areas that I want to talk about here. So we will jump into that because that's something that does interest me. But before we do that, I just want to talk about head gasket integrity. And this, anyone who's listened to our podcast for a while will know this is a pet topic of mine, reason being that back in my drag racing days, that kind of became the limiting factor or the fuse for how much boost and then hence how much power we could realistically produce from an engine. And particularly when you're dealing with production parts, these engines aren't designed to handle 3, 4 or 5 bar of boost pressure. So it really is a problem. When you're going billet with both the block and the head, does that just become a non-issue, or is it still something you need to factor in with your design?
I would say that is probably an even bigger issue with billet designs, unless you're specifically designing for that, because the designs sort of tend to be stiffer, which... Well, I guess it depends on what kind of a type of a head gasket you're running, really. But yeah, the sort of stiffer the design is, then the sort of less forgiving it is. Basically, if you don't have the sort of clamping forces sort of thought out correctly. So if you have a really high clamping force in some location, well, that's fine. The head gasket is not going to leak there. But then when you have a clamping force that is much lower at another location, then that's where you're going to see leakage issues or potentially blowouts, or depending on what type of a gasket you're using. So that is something that is actually one of the more difficult things to design for with our engines, at least.
The mainstream sort of thought process, at least for a mildly modified street engine that's turbocharged, would be, well, let's run an aftermarket MLS multi-layer steel style head gasket and an aftermarket stud kit, and we're just going to apply more torque to the studs, and that's going to hold the head down. Now, that works to a degree, but at least in my experience, particularly with some of the very high-grade materials, some likes of ARP for their head studs, the amount of torque we can produce or can apply to those studs and the amount of clamping force they provide, my concern has always been, are we clamping the head, as you've mentioned there, perfectly around the studs, and then having the relatively weak factory casting actually kind of bow out between the adjacent studs, hence actually fixing one area of a problem and maybe making the area between the adjacent studs actually more likely to fail. Is that what's your take on that?
That is basically how it works. So yeah, it's easy to think of like a billet block or a cylinder head or something like, I mean, these are really like stiff and you can like push it on it with your finger and it's not going to move at all. But then when you start sort of applying actual loads to the stuff, then everything flexes basically. Yeah. In addition to like overall how much engine torsion there is and all that kind of overall vibrations in the engine, then you have the cylinder pressures and the pistons rattling around everywhere and all of that moving around on the stuff. So, and then the clamping loads and the forces basically. So, since we're not going to have any video for this, so basically if viewers could like imagine if you take like two sponges and hold those against each other and you like clamp those with your fingers from like the outer edges, and then if we need more sealing in the middle of those and you just like squeeze the edges like further together, then that might actually make the sort of gap in the middle like even worse. So it's of course not that extreme, but sort of an overall sort of a view on how like the physics behind that works.
Yeah, I mean, I think I just wanted to raise that because most people would just consider that as a solution, just better quality studs and we're good to go. But we can actually get ourselves into a situation where we fix one area and make another worse, which sort of really comes down to it being a multifaceted aspect of the stiffness of the deck surface of the block, the head itself, and then also the gasket that we're using, which brings me to that aspect of it for high boost applications, particularly your Thor engine in a full-on drag application, 3,000 odd horsepower. What's your sort of preferred sealing method for head gaskets?
We would still be going with MLS as recommended for that. Definitely.
Okay. So no need for a sealing ring or O-ring or anything of that nature?
No, not at the moment. With our Thor engine, of course, we don't really have data for like really high power outputs yet, but we do have from our Rex engine that has been run with factory MLS gasket and run that to as high cylinder pressures as the team then testing dared run on that, and no issues with the head gasket at all. So okay. Fairly confident that sort of the philosophy and stuff like that we incorporate and the designs we do with that works as intended. So I don't think we're going to have a head gasket fail before we start getting other failures on components. Right. And of course, then if you don't have a problem with that, then of course running MLS gasket, you just basically reuse a gasket multiple times. You don't have any sealing stuff. You don't have lots of tiny details to put in place and stuff like that. So I think it's overall best solution. That also is really good for maintaining sort of a good sort of a head to block sort of interface. So when you clamp that down, you're sort of using the head to increase the rigidity of the overall engine package. So you don't just have like a single ring where you have like a really high force and then low force in other areas, but you sort of have some kind of a reasonable sort of distribution of that clamping, the total clamping sort of distribution to get as rigid a package as possible.
Right. Now, another question that I'm quite interested in hearing your take on, your experience on, I should say, really, is when we're assembling a billet block. Now, I've heard various conversations with people around required bearing clearances relative to a factory cast iron block versus a factory cast alloy block, and what we need to do there given the thermal expansion of the material. So what's your recommendations? Is this something you can sort of share with us, or is there anything special that actually needs to be done there? Is the clearances not really too much different to what we would expect with a factory alloy block?
It's not really that big of a difference. So it's mostly would be due to the thermal expansion rate difference between whatever alloy your block would be. Then if it's the typical 6061 or 6068, 6068. Well, I don't remember, but the two alloys that are typically used that are basically the exact same alloy. Or then the 7075 type that we're using. So those have a slightly higher expansion rate than the cast alloys, but it's not that big of a difference. But again, it depends. If you need to be able to start the engine cold started at minus 30 degrees in the Finnish winter for a rally event, then you might not be able to go super tight on the clearances. But other than that, I mean, basically would want to run really small clearances. It makes the sort of engine behave better also. The less sort of, the smaller the gaps you can run, so you have a less sort of amount of oil flow going through there. So you need a smaller oil pump and again, less heat into the oil system from the oil pump. And
So there's two very different design philosophies there around a bespoke race engine like your billet block versus modifying a production factory engine. So with a production engine, generally the rule of thumb is that if we're taking a factory engine and we're going to double or triple or quadruple the power and also run it significantly further in the rev range, and it sort of comes back to what you were saying before, that cast iron block or cast alloy block, when it's sitting there on the workbench and you're assembling it, seems nice and rigid, nice and stiff, nothing's moving. But of course at 10,000 RPM and 1,000 horsepower, there's so much force, so much pressure inside the block that all of those components do flex. So typically we build the engine with a slightly looser bearing clearance than the factory tolerance, just so that when the block and the crankshaft are flexing around, we've got essentially more oil between the crankshaft journal and the bearing surface, so we get away, or we reduce the chances of metal-to-metal contact. But as you mentioned, there's downsides with that. When we've got looser clearances, we need more oil volume to retain oil pressure. Typically, we'll also match that with a thicker viscosity oil from the get-go as well to get our oil pressure where we want. So that's not a problem because of your billet block.
So that the clearance stuff is a small trade-off. So if you run a larger clearance, you can't run as high forces through that bearing anymore because the contact patch is going to be more concentrated. But of course, when you're pushing stuff and crankshafts are flexing and stuff, you need to have enough clearance so that when block flexes, crankshaft flexes, that you're not like binding the corners of the bearings of the bearing surfaces.
It won't last very long.
Then it's going to be destroy itself very quickly and start melting the bearing, and can have the bearing like melt out in between like the surfaces, and that's not a pretty picture. But yeah, we've done lots of those in like the pre Elmer Racing sort of design days when we were just fooling around and having fun on circuit racing stuff. We've melted our fair share of bearings.
Yeah, normally it doesn't end up making you feel very good when that happens, because it's going to create a fairly expensive mess that you're going to have to fix. Okay, I just wanted to clear that up because this is a question we quite often get asked about bearing clearances, and just understanding that again, like I mentioned earlier in the chat, there's not a lot of black and white here. It's about understanding the specifications of what we're dealing with and the implications that drives, whether we can go tighter on our clearances and gain an advantage there, or again, with a production engine, that's probably not going to work in your favor long term if you're making very high power levels. I just want to talk a little bit about the validation of your design. So, before you actually produce the first Thor engine in its entirety, what do you do to kind of validate that, yes, this engine is actually going to work, yes, it's going to run in drag racing trim to, let's say, 10,500 RPM and 3,000 horsepower, and it's going to give a long and healthy service life?
Well, ideally, you would want to say, like, we looked at all the different details and calculated the oil stuff and calculated the heat expansion of all the components and looked at the valve train and what kind of spring stiffness there needs to be, and taken all the sort of potential misfires into account and all of that. And the reality is that everything is basically a guess.
Okay. Let me just clarify. A well-educated guess?
That depends on who you're asking, basically. But I guess some guesses are better than other guesses. Always, so something to take into consideration. But I mean, if we're being completely honest, I mean, there's absolutely no way to like properly design an engine at these kind of price ranges at all. To like, so this kind of comes back to sort of my view of the most cost effective way to develop something might just be to blow it up and see what blows up at what power level and under what conditions, and then you analyze that, and hopefully if you've done that smartly, so if you've been slowly building up to that, and then you find the limit, and then you know, okay, how far are we from where we need to be, and then you take it from there, basically. Because if you actually like looked at absolutely everything in detail, which you absolutely could do, but then it would probably cost somewhere in the range of like 2 to 5 million or something to develop one engine, and that's just not feasible at these levels. So you need to do basically every single thing that you think there's a good chance that you can get away with just a guess. That is a guess. Absolutely. And I'm not ashamed to say that, because that allows us to do these engines at these, like, I mean, compared to what they are at these insanely affordable prices, which of course compared to other engines might not be affordable, but compared to like a complete engine with these amounts, and so far so good. So I would want to sort of say that our guess ratio is better than what I've anticipated, and so far no failures. So we're waiting to see on what the first sort of failed guess will be.
Well, I guess no failures suggests that your guesses have probably been pretty much on the money so far. And I think just to come back one step, I mean, people listening to this, we do need to understand that you don't have a research and development budget of an OE manufacturer. So there's levels to this stuff. I mean, obviously, your engines are not going to be cheap by relative terms. There's an expensive billet engine that's had a lot of work go into the design and development, but yeah, that pales into insignificance compared to the sort of budgets that an OE manufacturer would put into producing a new engine. So that's what people probably do need to keep in mind.
Yeah.
These days,
that of course, depends a little bit. So I mean, technically, we are a OEM manufacturer because we manufacture the whole engine, specify all the parts, order all the parts and everything. Cool. But of course, the sort of quantity-wise, it's completely different. So if we're operating with a team of 3 to 4 guys and we do engine design in under 1 year with the first part ready, then if you look at some aftermarket, or not aftermarket, but sort of a factory race trimmed stuff for like F1 or LMP1 or something, they have tens of millions of euros budget and run sort of a development program of 2 to 3 years with 200 people maybe overall, or something in that size range anyway. So completely sort of different range.
These days with solid modeling software that's available, which I can only imagine you lean on heavily for the development of an engine like this. Finite element stress analysis is definitely something that these modeling software packages can do. Is that a useful technique to sort of validate these guesses, or is it just something you're not even worried about?
That is, I think, absolute necessity. I mean, we would not be able to do this at all without affordable 5-axis CNC stuff, affordable cam packages with FEM stuff, and it's absolute necessity. Otherwise you would be looking at having 50 guys drawing on pieces of paper and getting sort of specialized factories to do the casting stuff with expert casting guys trying to figure out from the drawings, like when you see old school F1 engine stuff from Cosworth and stuff. Those were but those guys were really good at their job. But having 3D CAD packages with FEM stuff, that's, of course, you have to be able to use those effectively also. Just getting those and starting to use them is not necessarily going to improve things at all. You really have to understand how things work overall, especially with the FEM stuff. If you sort of understand how it works and what kind of things you can calculate, what kind of sort of shortcuts you can take, what the results will mean depending on how you've calculated them, then you can be really, really effective. But if you're sort of starting to do design iterations, or you have to work with some external place, for instance, do the manufacturing and have some other place to help with the strength calculations, then your budget is going and time frame is going to 10x immediately, because it's going to be so inefficient.
So, I mean, over the last, let me say 10 years, I guess, we've kind of seen a number of manufacturers come on board with billet block and billet engine design components, or full billet engines, I should say. Really.
Yeah, that's nice.
Whereas at the start of my career, that just wasn't in existence. Back when I was drag racing with a Mitsubishi 4G63, there was literally zero option for a billet block. Now I could probably buy a billet block from at least a couple of manufacturers. So do you see that sort of relative explosion in billet engine parts and blocks come with the advancements in 3D modeling software and the relative affordability of that now?
I would think so, yeah. Yeah, in the last, I think probably in the last 10 years, sort of the main turnaround stuff. I think you could probably have done that 20 years ago, 25 years ago, maybe, if you were on the cutting edge of stuff. But things were so expensive then that not sure really how cost effective it would have been. But yeah, especially in the last 10 years, you can get affordable CAD packages. And if you sort of put the time and effort and sort of the mental attitude into really understanding how things work, then you have been able to do this stuff. And I think that's one of the reasons why we're here also. So really happy about that progress.
And I think it sort of everything progressed at the same time, though, because relatively speaking, 10 years ago, we didn't have people, and I'll focus here on drag racing because that's sort of the area that I probably had most exposure. We didn't have people producing sort of 3,000 plus horsepower from a Toyota 2JZ. There weren't cars, import cars running 5-second quarter miles. The turbo technology wasn't there to allow the power levels that we're seeing now that actually almost certainly require a billet block. So, there wasn't necessarily the requirement for those parts back then, and the whole industry has progressed both with the advancements in the electronics for engine control, the advancements in the turbochargers, which have allowed us to make more power, significantly more power, and then we get to a situation where the billet block almost becomes a necessity in some platforms if you want to actually hold it all together. So it's sort of been a nice synergy the way everything's developed and sort of come to a head in the last probably 5 or 6 years at least anyway, I think.
Yeah, I think that's one of those things where when the overall package sort of starts going, then all the sort of different parts sort of keep pace and try to evolve pretty much at the same time, because there's no need to develop one of the parts if four other things need to happen at the same time, and those are nowhere near happening. But then when four of the other things are moving forward, then the fifth thing sort of keeps pace also, and then everything keeps moving forward.
Yeah. I think that's exactly it. One more part, just while we finish up on the Thor engine here. I think it's easy for our listeners to sort of think, okay, well, I've got a 1,500 horsepower engine now that I can go circuit racing with, or 3,000 horsepower for drag racing. So I'm done, right? We don't even need to worry about that engine again. I assume you still have a required maintenance schedule at whatever power level this engine's been run at. Could you talk to us a little bit about what maintenance is required and maybe sort of what running intervals?
So it is, the timing or the cam drive, of course, needs service regardless of what kind of construction that is. So our Thor engine uses a belt for that. So regular sort of service for that. If the belt starts looking that there's some corner or something that looks a little bit worn, then it needs changing. Internal components, the connecting rods on that. So we currently only have aluminum rods available for that. So especially for circuit racing use, that should theoretically limit their lifetime, but that's a little bit unknown at the moment, how long those will last. So RP968 has run the most hours on the engine so far, and as far as I know, haven't had any issues with those yet. And that is also something that we can sort of look at a little bit without having to disassemble the complete engine. So we have a service patch cover or something like that underneath the engine where you would typically have an oil pan. So we don't have an oil pan at all. So we have a cover there. You can remove that and pull out the bottom halves of the connecting rods and inspect those. Look at the bearings. Look at how if you see. Well, I would guess if you start seeing large cracks, then I think they probably would have failed already, but not really sure. Sometimes you might catch that opportunity. So sometimes you might be, depending on what the geometry is, where the cracks start propagating. Sometimes you even see things that start cracking and then they crack to a certain distance and then they stop cracking there. And then you have a big design problem because you have lots of extra material there that doesn't need to be there.
So I want to talk a little bit about that. I didn't actually realize you're running alloy rods in that engine. And I mean, in general, I think it's fair to say that alloy rods, for the most part, are only really used mainstream in drag racing because the material does have a fatigue life. So basically, at some point, the aluminium rod is going to end up failing, and obviously, when you have a rod failure, that gets quite expensive. And I've talked to manufacturers such as GRP who make these alloy rods, and it's really hard to pin them down on what the lifespan of these rods is likely to be. That they kind of get a bit slippery when you start asking questions around that, and understandably, I mean, there's a lot of elements that come into this, the stroke, the RPM ceiling, the specific power level, cylinder pressure, and obviously then runtime of the engine. So
it's really impossible to figure that out really, because the load case is so complex that you can't really simulate that and do any kind of reasonable calculation for that. I think what the most sort of pushed components would probably be like F1 components from the V10 and V8 days, when they were really pushing the RPM, and they had like 100 RPM margins, like, okay, you can stay this long at this RPM range. So I would assume that they like test those to destruction, and then sort of have some kind of a curve fit from there, and then sort of start to figure out like how to do that, because there's absolutely no way you can be that accurate with any kind of modeling. So yeah, it's entirely understandable that for manufacturers of rods or stuff like that, it's not feasible to be able to like give any kind of even like good estimates on that.
I think most people just sort of err on the side of caution and decide that replacing a set of rods once a season or once every 50 passes down the strip is probably cheaper than windowing a block when things go pear-shaped. Yep. So I guess that's what most people do. On the other hand, most people probably would shy away from fitting these rods to a circuit race engine for that reason, the unknown sort of life expectancy. I'm assuming the reason you went down that direction is the reduced mass of the alloy rod over a steel rod?
Not really. It depends on what kind of stiffness you need, because it's much easier, of course, to get alloy rod to be stiffer at the sort of same weight, because you have the sort of a mass to stiffness ratio from aluminum to steel is basically the same, but because of the aluminum rod being what is it, like half the weight, 1/3 of the weight, something like that. I don't even remember anymore. Oh no, how embarrassing. But anyway, so that makes
That's not a test.
But yeah, so the aluminum rod will be much thicker, and that makes it much stiffer, like bending wise and all of that. So that means that the bearing life is going to be much better and all of that with the same mass. But the main reason we went with that with Thor was we were looking at a custom rod. We needed to get that. What was this? This was almost close to 5 years ago already. Wow. It seems like it was like 500 years ago or something. Okay. But anyway, so yeah, we were looking at rod manufacturers, and no one really wanted to say that their sort of steel rods could do anywhere near the sort of cylinder specific power we needed from that. So yeah, we ended up going with aluminum rods, and we were in a time crunch. But now we're sort of more stringent on that, and sort of shopping around for rods for our Hell engine currently, and have maybe a lead on that, and hopefully we'll be running steel rods now for drag racing use. So tables have turned.
Okay. All right, so that's probably a nice time to segue into the Hell engine, which you've mentioned a couple of times already. So this, as I understand it, is your sort of take on the Nissan R35 GTR engine?
Yeah, there will be a complete bolt-in replacement, which kind of a loosely termed bolt-in. So exhaust port location has been moved and resized a little bit, and will require different sized intake manifolds and stuff like that. But exterior dimensions are the same. Bolt pattern for the bell housing is the same. Front drive setup will be exactly the same. Will be dry sump as all our engines have currently been, and again, of course, pushing the displacement as much as possible again.
So the R35 drag racing market in particular, which I'm guessing is where this engine is sort of focused, is really mature, and there is a huge amount of competition in that market, with at least a handful of manufacturers making their own billet blocks, power levels around the 3,000 wheel horsepower, I guess, for some of the top teams I've spoken to at least, and maybe there's some making more than that. Where did you see a gap in that market? Where do you see the weaknesses of the current offerings, and what do you think you can bring to the table that's going to be superior to what's currently on offer?
Well, I would like to say that, we had a research team look into that and figure out the sort of market opportunities and what kind of cost benefit we could provide for that. But no, in reality, it was just a question again of a customer talking us into making that engine really. So that's how we ended up with that. But of course, we did look into that, like, because it doesn't make sense to just make provide a couple of engines and have one for ourselves to test or something like that. That wouldn't be cost effective at all. So we did look at that a little bit, and I did speak with some of the top or current fastest GTR sort of stuff, like over in Dubai, a couple of places, and spoke with a few other people, but the sort of longevity wise, what they can push from that and how that package works, I'm a little bit tentative to see, like, if we could, like, actually do 4,000 horsepower. So that is around 1,000 horsepower more than what the other engines are currently sort of making. Yep. But if the drivetrain on a R35 is going to be able to take that is a bit of a question, because they're already like pushing the disc amounts in the clutch packs really far, and they have sort of a gear shift time limitations going from second gear to third gear, and all this stuff. So adding a huge amount of power to that might not actually make the cars a lot faster. But again, you can run much larger turbos with increased displacement and much higher, much larger valves and a higher flow on that. So it should be much easier to run the RPM also lower while still sort of maintaining the turbos in the sort of operating range. So there might actually be benefits in that regard, not just sort of power wise, but also sort of being able to go lower down in the RPM range, and that will like help launches and maybe allow for longer gearing or something. But some question marks.
So obviously the stock VR38 3.8 litre V6, and then we see there's a variety of kits, but sort of let's say the billet blocks for drag racing use maybe around the 4.2 litre capacity, or thereabouts at least. What sort of capacity are you targeting for this engine?
So we're going with 5,000 cc with this, or it's like I think 1/3 of a cc below that, or something like that is the accurate number for that.
Sure. Okay. And where do you sort of see the current weaknesses in the billet VR38 options? Where do you sort of see the areas that you needed to focus on improving in terms of getting a better result over and above just purely the additional capacity?
So really the valve size and cylinder heads, and then the crankshaft longevity are really the main things. And the crankshaft is actually a really, really big headache with that engine. Of course,
V6 makes that tricky, doesn't it? With the size of the big end bearing size.
Yeah, 660-degree even fire V6 engine is absolutely horrible for like balance wise and crankshaft stuff. And size wise, we could push the displacement further, but then we can't fit enough counterweights on the crankshafts anymore. So we're basically limited by crankshaft counterweight amount to the 5,000 cc displacement, which is kind of interesting problem.
We talked to JR from ETS a couple of years back at Airstrip Attack at Pikes Peak, and just getting some data around sort of the longevity of their engines at 3,000 wheel horsepower, and I forget the specifics now, but I think he was talking about the crankshafts they are running, which I think off the top of my head were Sonny Bryant billet cranks, sort of just about the best that you can pay money for, and I think they were getting something like 6 to 10 or 10 to 15 passes out of a crankshaft, and maybe 15 to 20 passes out of the valve train or rotating components. These engines were just eating up expensive parts, but the crankshaft you've just sort of focused on. So is there something you can do that's going to appreciably improve the life expectancy of a crankshaft in a V6? Like you say, it's a design problem, and you want to make 4,000 horsepower. So what can you do to keep that crankshaft alive for longer?
Yeah, so that is something we're basically first of all going with a design sort of similar to our Thor engine, where we have like sort of the shape of the connecting pieces between the bearing surfaces is highly optimized and smooth and designed, so there are no like flat surfaces that are just like milled down, and running piston guided rods, of course, so that we don't have the lips around the bearing surfaces to get those as smooth of a transition as possible. But then also we have to go to a larger diameter bearings for those, and also more narrow bearings, so that we have more space between the bearing surfaces for like a more sort of a design freedom for the shape there. And also we have to go with a higher strength alloy also compared to our Thor and Rex engines, because that 60-degree V6 engine is absolutely horrible design. But that is what will fit into a GTR, so that's what we have to go with.
Yeah, I mean, there's some elements you're stuck with. I just want to go back and talk about a few of the elements you mentioned there. So you talked about piston-guided rods. So you're talking there, in most engines, the big end of the rod is located by essentially cheeks on the big end journal of the crankshaft, correct? And you're doing that the opposite way? Yeah.
So the piston has like a much smaller gap to the connecting rod, and that basically keeps the sort of the piston of course stays in the bore, but keeps the sort of a connecting rod sort of centered in the bore basically, and that means that we don't need the lips on the crankshaft, and that means we don't have the sort of smaller radius issue there, and that allows us to run sort of much more evenly loaded crankshafts, so it will be much more durable. In addition, of course, to the other changes that we also had to do.
Yeah, well, the other one I wanted to talk about there, which would probably sort of go in the face of normal convention. You mentioned you've gone smaller on the big end bearings. So normally
more narrow, but larger diameter.
Larger diameter, but narrower. So that's just giving you more material between the adjacent big end journals on the crankshaft to improve the crankshaft strength, correct?
Yeah, and also between the counterweight and between the big end bearings also for the cylinders in like the same pocket. That is absolutely necessary. Like looking at the design, like I have absolutely no clue like how the factory type crankshafts are even holding together at all. But okay, if they could do like 10 passes at the power, then okay, that might like be. But it's of course one thing when you're pushing something to the absolute limit, then you can like push things so much further. And if you're designing something to be able to hold to something for some amount of power, then it's like a completely different sort of aspect on the sort of tolerance range where you're operating in. So if I'm like designing something to be able to do 4,000 horsepower, then okay, it's not of course a guarantee that it will hold for 4,000 horsepower, but I want to be relatively sure that that is going to work with that. But then when you're actually pushing that component, you might push it to 5,000 or 6,000 horsepower or whatever, and then it will still do like 40 passes at 6,000 horsepower or something. But it's a completely different thing than like designing something for a specification.
All right, a couple more elements I want to talk about on this engine. So just bringing back an earlier part of our conversation, you mentioned a plasma coating on the raw alloy as opposed to a sleeve. So again, I think at least in my experience, engines at this sort of power level in the aftermarket, that isn't something that I think too many are doing. What was the driving sort of force behind that versus a conventional sleeve?
Well, basically the sleeves just like eat up useful space in the engine really. And instead of having the sleeve, you can just delete the sleeve and run a larger bore instead. So that again allows you to run larger valves and overall sort of run larger displacement at a higher RPM, making more power really. So really want to push that further. You
don't really need that sleeve in terms of the strength. That's not the issue. The alloy that you're running has sufficient strength, so you don't need the sleeve for the strength aspect, and that kind of feeds back into what you were saying about making that sleeve thinner earlier in our conversation. But the issue, of course, is we can't run the ring directly on the alloy, so the plasma coating just allows a harder surface that ring can then bed in and run against. And that is what Nicocell has been used for also.
looked into potentially doing Nicosil stuff also, but we also actually found that it was easier to find plasma spray stuff for that. And plasma spray should also be more durable than Nicosil coating and not have the sort of same sort of chipping issues and stuff like that you can run into with Nicosil stuff. And you have a much sort of wider range of material that can be plasma spray coated also onto the cylinder. And yeah, comparing to the factory GTR engine, VR38 also has plasma coated cylinders. And well, those are actually, I think they run those factory blocks up to like 2,800, 3,000 horsepower, something like that with those. So yeah, I think we're fairly confident we can stretch that a little bit further.
From our conversation with Tony Palo from T1 Race, I think it sort of came to be that people were prematurely jumping to a billet block on the GTR platform thinking they needed to. And realistically, he said he hasn't found the limit of the VR38 factory block. The only reason they go billet is because they need more capacity for what they're doing. So it's actually not the limitation that many people maybe thought. Now, the next part is these billet heads, which obviously sort of is a recurring theme with your race engines. And to the best of my knowledge, I don't think anyone else is doing a billet head. I may be wrong on the VR38 platform, but that gives you a lot of flexibility. Obviously, you can do then anything you want. And you've mentioned a couple of times now how critical these bigger valves are. And I guess ultimately, the engine is just an air pump, and the valve size is going to be one of the bigger factors limiting airflow in and out of the block. So optimizing that obviously makes a lot of sense. But there must be a bit of sort of weighing up here. Obviously, the aftermarket parts industry for the VR38 is very mature. There's a bunch of different options for exhaust manifolds. There's a bunch of different options for inlet manifolds. And from what you were saying before, someone running your engine is going to have to sort of start from scratch on that. So I assume going down that path, you're expecting a massive improvement in performance for that downside and needing to come up with these new components.
Yeah, definitely. I think we will be able to push a lot more power from this engine compared to the VR38, especially looking at the exhaust ports on the factory heads. Intake ports also a little bit. So yeah, one of the sort of main limiting factors there is apparently they need to make the engine really narrow to be able to fit into the engine bay of the R35 there. So that in the cylinder heads, for instance, they have really, really short valves, which creates a big problem for the geometry for the exhaust and intake ports. So you have a really small sort of a short side radius on those, which means basically you're not really getting any flow on that side at all. Mm-hmm. And ultimately, even though sort of we don't really like to sort of get on the sort of a valve flow or head flow bandwagon. We think that's way overhyped compared to how important other factors are in the engine. But ultimately, if you're not sort of talking strength-wise, then the valves and the ports are ultimately going to dictate how much power you can make. The displacement only says at what RPM that's going to be happening at. So by improving the sort of port flow and valve size, that is really one major improvement, and I think we can get a big improvement on that. And we're also, so this is the first engine now with due to the super short valves, where we're doing a contoured intake and exhaust ports, where we're contouring the port shape around the valve guide and around the valve spring pocket on the intake side. So those give some really sort of a high tech and nice looking ports, but it's not just for show; it's actually required because of the short valves.
Sure. Okay. In terms of the rest of the valve train components, camshafts, etc., are you backward compatible there with the existing R35 GTR componentry, or is everything there bespoke?
We will be fully compatible with that. Yeah, we are running larger buckets to be able to run custom camshaft with a larger lift, but the lobe location and all the bearing size and all of that is factory compatible.
Okay. Again, with such a mature market for things like aftermarket cams for the VR38, I guess that's something you need to factor in that makes sense to retain.
Yeah, definitely. That is also something we looked into a little bit, like what kind of sort of castings are available, or like I don't remember what they're called, like the blanks that the camshaft manufacturers sort of grind the or finish the lobes from, like what kind of lifts they have available for those, and yeah, they are we've found one manufacturer actually that does have according to them, significant amount of extra material there to increase the lift. So we have accommodated that on the cylinder head design to allow for larger lobes than what can be fitted on the factory engine.
Okay. How far away are you from sort of sending one of these down a drag strip for the first time, or at least maybe heading to the dyno for the first time?
That will probably be February, March, something like that, I think, is what I was looking at
Not far away.
Yeah.
Okay. Exciting. Oh, I look forward to watching the development of that and see how you progress. It definitely sounds like an exciting platform. Right, I think we'll head towards wrapping this thing up. Oskar, we've gone a little long already, but it's been a great chat and some exceptional insight. What's sort of next for Elmer Racing? What do you sort of see for yourself in the future and the direction that you're heading?
Well, sort of overall, I think, well, for the current Elmer Racing stuff, probably doing bespoke engines, maybe one-off engines for like concept cars or supercars or stuff like that is something we're maybe looking into, because now we have enough data from different engines already that we know, okay, we are kind of relatively good at guessing on enough engine things to be really, really cost effective at doing custom engines. So that is something that we're looking into, and we've actually been contacted by multiple supercar manufacturers, but nothing sort of moving forward yet at the moment. There's also something that we want to be relatively picky about choosing the right customers, because we've been bitten a little bit by jumping on the sort of wrong customers too early. So trying to be a little bit more conservative on that aspect now. But overall, sort of using our engine design stuff, we really want to get into doing aviation engines, and that's actually I was just a couple of weeks ago in Dubai there for the Dubai Air Show, and I was at the industrialization summit there, and networking and trying to find contacts and stuff like that to get that ball rolling, really. And that really
interesting.
Really sort of started out from looking at the Thor engine, where we concluded that it's actually like too powerful for circuit racing use, that, and the power to mass ratio is, I mean, as far as I know, the best of any OEM circuit racing engine ever, including all F1 engines. We're like looking, well, we don't really want to reduce that, because I mean, having a good power to mass ratio should be like a positive thing.
Definitely,
and, so aviation engines would definitely be something, and the numbers do look really good, and that's something we're trying to sort of work out and go. But that would be a daughter company, of course. Elmer Racing would continue operating as currently.
Yeah, I recently passed my private pilot's license, so I've been messing around with general aviation and light aircraft for. It started about 25 years ago. It's been a slow process, but I finally ticked that one off. And one thing that, obviously, with an engine and a tuning interest in my background, I've always sort of been disgusted at the technology of the general Lycoming or Continental general aviation engines. I mean, they do a job, and they're reliable. And let's be honest, we want reliability in a light aircraft, but the technology just isn't there, and the fuel efficiency and the power leaves something to be desired. So I'll watch that space with some interest as well.
Yeah, I think there's definitely something to be improved on there. So both with the, I think with increased technology, you can also push the sort of fuel economy and power envelope much further while maintaining reliability because of the added technology also. So.
Yeah, I have no doubt it's an area that's rife for upset, and it would be definitely good to have a little bit of improvement in fuel economy and power. I don't think any pilot would be against that. Now, what advice, I guess, if you could go back in time now and advise a younger version of yourself looking at setting out on the career path that you've had over the time you've been involved in the industry, what advice would you give yourself to maybe fast track your learning and your experience?
Ooh, that's a tough one, really. There are like so many different things that you could kind of do better, but then again, if you like would have made a different choice, then it's like difficult to see like what that path would have led to, for instance. So really
Understood.
hard to say. But of course, I mean, some general things like really figuring out like how much budget is needed for some type of a project or something. Like, is it worthwhile to do that or not? Because yeah, to be honest, we didn't really have the budget to really start our company or really have the budget to develop any engines or anything like that at all. But here we are anyway. But I think we are basically probably 3-4 years behind or something because of basically budget constraint issues. So that is definitely something that I would sort of try to sort of tell myself to focus on and think a little bit more about that aspect and have some kind of maybe future plans also, but of course also still be open to modifying those.
Yeah, I think that's solid advice. I think particularly when you're young in this industry and you don't have the experience, and obviously that's where we all start out, you're in that situation that you don't know what you don't know. And I would imagine, even dumbing this down to a project car level, the number of young guys and girls who get involved in building a project car without a real solid understanding of what the finished project that they've got in their mind at the outset, what that's actually going to cost. And I've been guilty of this myself. You get involved in starting a project and sort of 6 months in, you realize that you just don't have the budget that this car build requires to do it at the level. And that if you're not conscious of that at the get-go, it can do a couple of things. It can end up being quite disheartening, and often we see projects end up getting abandoned because there's just not enough progress on it. Or alternatively, you end up with a project that just spans the next decade, which isn't a lot of fun, and you get stale on it. So I think being really as realistic as you possibly can about what a particular project is going to cost is smart. And I mean, there's always people you can bounce ideas off to get a better idea of that, people who have been down that path before and already have the runs on the board. Yeah,
but then also, like, if you look at it in that aspect, there probably would be a lot of projects that wouldn't even have started or wouldn't have learned anything from that. And because if you conclude that you need X amount of budget and you don't even have anywhere close to that, then it's not going to happen. Are you going to blow up enough stuff to like learn things effectively? But then you of course need to be careful about not blowing up things that are too expensive that you can't like recuperate from, because that is then it's going to slow down the learning process a lot. So, but I would also think that maybe being sort of more confident and sort of not expecting everyone else to have the sort of same knowledge level. That's maybe one of my sort of personal sort of downfalls. When I'm talking to someone that supposedly is an expert, then I said, okay, like immediately assume that, okay, like they're sort of equal and have thought about all the different things and sort of the same amount of level and thought about different varieties. Of course, they probably will have lots of experience with data, but they don't necessarily understand how that works in different situations and can like apply sort of knowledge to other things. That I think that is one of my like personal strong points, is being able to sort of understand the overall picture and how sort of values apply in different conditions and okay, like this works here, so that means in this condition we can like do 10x that, or in this condition, okay, we need to be super careful about that because the temperature is like the limiting factor and we're having slightly higher temperature, so we need to reduce this whatever quantity by 20% or something like that. And like figuring out how things apply to different levels. I think I've wasted a lot of time and had a sort of some sort of a really bad customer experiences based on sort of overly trusting sort of other people's judgment that don't necessarily sort of understand the topic, but sort of balancing out and being more confident is one thing I would definitely think that would have sort of a benefited sort of having that attitude much earlier.
Oh, yep. All right. Last question for today. If people want to follow you or find out more about your products, where are they best to do that?
Well, we try to update stuff that we work on, but we sometimes do a better and sometimes worse job of that. So, but yeah, we do. So our website, elmerracing.com, we do have links to our social media there and also to our web shop. So shop.elmerracing.com. We're on Twitter, YouTube, Facebook, and Instagram, which we update sporadically, completely at random. So yeah, if you want an overall picture, then basically you have to follow every single social media to gather the information, because we're really bad at sort of putting together a package so you can just follow one social media. But yeah, that's something we really need to work at. But we try to update some stuff anyway.
It's hard when you're that busy designing and developing world-beating engines. So we'll cut you a little bit of slack for that, Oskar. All right, we'll drop some links in the show notes anyway, so people can follow those to find you. So look, we'll finish up there. Oskar, thanks again for a great chat. Been really insightful, and we look forward to seeing at least the development of the RP968 at World Time Attack in 2022, and I'll be keeping an eagle eye on the R35 drag racing scene to see how your engine stacks up once that gets released.
Yeah. Thanks for having me on the podcast. Super nice chatting again. And yeah, I think sort of me going off track all the time and you sort of reeling that in a little bit and keeping things under control, I think makes really good stuff for viewers. So,
all right. Thanks again. We'll talk soon.
Yeah, thank you so much.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.